Hi guys, we are group number 3. Today we are presenting about evaluating multiple reinforcement learning agents in the frozen lake environment. We have two focus, scalability and stochasticity. As you can see here on the left, we are using Frozen Lake Gymnasium environment. We have 4 actions, moving left, right, up, and down, and our observation space is depending on the size of the map. We're gonna give you 1 point if you reach the goals, or we're gonna give you 0 point. To introduce randomness into the map, we have slippery variable. If set to true, the player will move in the intended direction with prop 1/3. The reason why this problem matter is because um, the scenario tests how reinforcement learning algo adapt to randomness and large state action space, which is critical for real-world application. So we have two different hypotheses. Firstly, we hypothesize that at the gradient increase, function approximation method and policy gradient algo will perform better than Q-learning. And secondly, we hypothesize that when the environment is stochastic, policy gradient method will show a greater adaptability comparing to Q-learning and function approximation. And to test the hypothesis, we evaluate 5 different agents, random Bellman, Q-learning, function approximation, reinforced, and actor critics. We're gonna run 2 different experiments. Firstly is to test agent on 2 grid size, 4x4 and 5x5. And secondly is to evaluate it under deterministic and stochastic conditions. And for all of the experiment, we're gonna run with training over 5,000 episodes.
And after training and evaluating our agents, we have 3 key takeaways. Our first key takeaway is that policy gradient and functional approximation methods are effective for scaling to larger environments. So we have the training rewards plots for all agents in 2 different grid sizes. And for the 4x4 grid, all agents except for the random Bellman perform well, reaching almost a perfect score. Then when we scale up the environment, reinforced actor critic and functional approximation agents perform similarly well. However, the Q-learning agent's performance decreases. And our second takeaway is that stochastic environments challenge tabular methods, but functional approximation shows surprising strength. We set the slippery parameter to make it a stochastic environment, and similar to the last takeaway, the Q-learning agent struggles, as you can see the decrease in the performance of the Q-learning during training on the left, and the evaluation on the right as expected. However, one surprising finding was that despite our hypothesis that policy gradients would perform better, functional approximation actually showed the highest increase in the performance, as you can see from the evaluation reward on the right. And our third takeaway is that actor critic stands out as the most consistently reliable approach across all settings. As you can see from the table for evaluation rewards for all agents under different settings, the actor critic agent steadily performs well relative to the rest of the agents, reaching a high score that's close to 1 in all settings.
And those takeaways lead up to our conclusion. So for the first hypothesis, the results were mostly consistent with the expectation. So the policy gradient method, especially actor critic, show a strong scalability in larger grid environment. In contrast, Q-learning struggled to generalize, with its performance declining significantly. For the second hypothesis, the results were somewhat mixed. So while actor critic and reinforced demonstrate adaptability, the function approximation method also works surprisingly well in the stochastic setting. In the meanwhile, the Q-learning performance declined under this condition.
Here is a little snippet video of our actor critic agent on the 5x5 grid under slippery condition that reached the reward successfully. And that is it for our presentation. Thank you for listening and have a nice winter break. Thank you.